Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the complete guide to Reynolds number. This is the first video in our March competition whereby you can earn £1,000 a month every month for an entire year. So be sure to check out the question at the end of this video. So the first question we have to ask ourselves is, what is Reynolds number? And Reynolds number is probably one of the most important and most common dimensionless numbers that we use in chemical engineering to determine and categorise the nature of fluid flow. And it's governed by the equation denoted by RE, so that's for Reynolds number, is equal to rho Vd over mu. Now there is some variation in the formula, but that's the general formula. And rho represents the fluid density, which is in kilograms per meter cubed. The V is the fluid velocity in meters per second. D is the pipe diameter in meters, and the viscosity is mu, which is in kilograms per meter second. Now what you can do here is you can actually perform a unit balance, so by substitution of the respective units into the formula, and you should see that all the units cancel themselves out. So again, you could try that in your own time just to prove that it is indeed a dimensionless number. Alternatively, we also have what's called a dimensional analysis course. It's a free course. I'll put a link in the description to that, and there is a method known as the Buckingham Pi method that allows you to derive an extensive amount of dimensionless groups. So again, I'll put a link in the description to that if you are interested. Now, if we take a look at the actual proof here, then what we can see is by sheer manipulation of the units here, we have kilograms per meter cubed times meters per second times meters. So they meters will cancel each other out, and that'll leave you with meters. So you have kilograms per meter second, and wouldn't you notice that these are exactly the same on the top and the bottom, so they become unitless. Now, a more generalised way of expressing Reynolds number is essentially to find the ratio between what's known as inertia forces divided by the viscosity force. So granted, it's only the viscosity on the denominator, but the inertia forces basically account for the way and how it actually flows. So what I mean by that is it accounts for the speed. So we have the velocity in here as well, and it also takes into account the geometry of the system as well. So that's what we mean by inertia forces. Now let's have a look at this in some more detail, because we will look at this in a couple of different ways. We'll explore Reynolds number quite extensively. So the first thing that we really need to look at is the three categorizations that fluids can fall under. And it's based on what Reynolds number actually is. So there is some ambiguity as to what the actual values are for these three criteria, and it varies from source to source. So different published literature will give you a slightly different value, but you will find that they are within say a 10 to 15% error tolerance of each other. So you can expect within that kind of range. Now the first one, or the first condition, is we have laminar flow. So laminar flow is very steady, it's very uniform, and it's very calm. And that occurs whenever a Reynolds number is less than approximately 2,300. We then, between 2,300 and 3,500, we enter what is called the transitional flow region. And there is big ambiguity here as to where this actually begins and where this actually ends. So depending on the source that you use, the transitional flow can sometimes be neglected, other times it is taken into account. But generally we're speaking between Reynolds values of 2,300 and 3,500. Which then leads us to the final type of flow, which is turbulent flow. And this is a very randomized, very chaotic type of flow. One that is very good for certain operations, such as heat transfer. And that occurs at any value above 3,500. So anything above that threshold, you will be in the fully turbulent flow region. Now, if we look at this on a graph or in a pictorial form, then if we start from this point here, so we start from down here, then we have this uniform velocity profile, and between this point here and this point here, we are in the laminar flow region. So you can see that the arrows are very streamlined, all right? That's what this key means here. So straight arrows indicate we have very streamlined flow. So it's very ordered, it's not chaotic, it's very predictable in its behavior. But as we tend towards turbulent flow, we get in this small transitional region, you can see that the arrows begin to bend. Now, they don't turn fully turbulent until we reach Reynolds of 3,500 or greater. But what you can see here is we start to form these non-linear characteristics within the fluid. Once we reach the turbulent region, you can see that we start to get this very chaotic mixing of the fluid. And essentially what we would call from this layer forward is the fully turbulent region. Because what we actually have here, and this is a strange phenomenon that can be quite hard to get your head around to start with, but at the point that it touches the plate, so when your fluid is fully adjacent to the plate, we actually call that the non-slip velocity. So at the plate, we actually have a velocity profile of 0. So it remains pretty much laminar, even if we are in the fully turbulent region. It just, because the turbulence is so big in comparison to this small region, it is neglected. But you can clearly see that the arrows remain fairly laminar, but in comparison to these, they are heavily outweighed. So anything above the 3,500 threshold, we would have the fully turbulent region. And this gives you a wide range of characteristics. For example, it allows us to conduct heat transfer a lot quicker. It's more efficient. It allows us mass transfer to take place a lot better than, say, in the laminar region. Now, these circles or arrows, these can often be referred to as eddies. And you can get very large scale eddies, for example, a hurricane storm, or you get very small eddies like the vortices in, say, a river, for example. But that's the technical name for these types of systems. Now, laminar flow, if we will look at these individually, laminar flow is categorized by streamline, steady and well organized. And we often use the velocity and the stress distributions to better understand this behavior, especially within pipe systems, because ultimately when we design processes, we're often working with fluids. And we want to know what type of flow we have, because there will be different equations that will describe and characterize the different types of flow. So if you have been familiar with fluid dynamics before, then you would have seen the figure previously, and you've probably seen this figure as well. But if you haven't, and this is your first time, then I'll go through this step by step. But essentially what we have here is this is a plot and a representation of the comparison between the velocity distribution and the stress distribution. So if we consider the velocity distribution first, then what we have here is at the center point, so our flow direction is going from left to right, then the flow at the center of the pipe is at its greatest. So this is the fastest part of the flow, and because it's laminar, we have this well organized streamlined flow. So we know that it's pretty much going to be symmetrical on both sides of the pipe. But the interesting thing here is that as we tend towards the pipe wall, our velocity gets less and less and less, because we then start to have some resistance and some frictional forces from the pipe wall. And that point there, right at the point of contact, we actually have a velocity of 0. That's our non-slip velocity profile. So anything after that, the resistances get less and less and less until the point in the center that we have our maximum velocity. In conjunction to that, if we think about it in terms of the resistance to flow, then at the centre point, that is the least amount of resistance. So the stress distribution is pretty much zero. So when we have maximum velocity at laminar flow, we have minimum stress distribution. Whereas when we have a non-slip velocity, or a velocity of pretty much zero, we have maximum stress distribution, because that is resisting the flow from going from the left to the right. So that's the interpretation between the velocity distribution and the stress distribution charts. If we look at it in the context of turbulent flow, then turbulent flow causes significant amount of mixing within the system, and therefore the velocity profile becomes much flatter. And this essentially allows us to balance the random forces that are occurring within the body of the fluid. So as a means of comparison, this is as for laminar flow. So you see that we have a very parabolic shape, which we've seen in the previous figure. But when we have turbulent flow, because we don't have that streamline or that steady type of flow, the vortices actually basically bang into each other. So they actually prevent this maximum parabolic shape from occurring. So you get a very flat head. And because of the power behind the fluid flow, you don't tend to get the same types of resistances as you would do, say, for the laminar flow. So that's what you could expect to see inside a pipe for both types of flow. Now again, we can represent this graphically as well. So if we consider the plot of velocity versus time, then we can get a better understanding as to the predictability behind it, because when we have laminar flow, we can predict the behaviour of the fluid pretty well. But in turbulent flow, it is pretty much impossible to do any real predictions. So that's why when you see correlations that involve turbulent flow, they're often more approximations, and they often require the use of more variables in order to account for this randomization. So if we look at the effect of the velocity as a function of time, then you can see for laminar flow, we can pretty much say that at any given point, we would know what the velocity is at any given point in time. Transitional throws some variation, but not very much. So we still get at points this laminar behaviour, but we're getting these small regions of turbulent activity. So this is becoming unpredictable. And when we get to turbulent, you can see it is clearly impossible to create a predictable model for turbulent flow. Because, for example, if we were at this time here, then our velocity would tend to this value. But yet if we come here, or indeed here, at a lesser time, then our velocity is even greater. So the predictability is not there. Now the relationship with pressure drop, because when we have the fluids flowing within a closed system, i.e. a pipe, then one of the key constraints is what is the pressure build-up and what is the pressure drop going to be within this particular system. And any fluid dynamics module, any fluid dynamics course will always consider and put great emphasis on pressure drop. So we can describe the pressure drop of any fluid within a pipe using what's called the Darcy-Weisbach equation. And it's denoted by this equation here, where we have delta P over L. So what this actually tells us is this is the pressure drop per unit length. So normally, for ease of simplicity, you would do it as 1 meter. Right, so that we could understand what the pressure drop is every meter within the system. Now the difference here, now this applies to any fluid flow, whether it's turbulent or laminar. The key distinction here is the value of F, because the density isn't going to change, the average velocity isn't going to change, and the diameter of the pipe isn't going to change. So we have to account for this distinctive parameter called the friction factor, because the frictional forces will be different depending on whether you have laminar flow or you have turbulent flow. you will have greater frictional forces for turbulent flow than you will for laminar. So we have to take this into account. And the way that we do this is we have to find the friction factor as a function of Reynolds number, because Reynolds number tells us the type of flow regime. So if we have a laminar flow, then the friction factor is simply 64 divided by Reynolds number. Now these are empirical formulas that have been derived from several experimental data sets, so you would never be asked to prove this, but if you have laminar flow and you want to work out the pressure drop within the system, for your frictional forces it is simply 64 divided by the respective Reynolds number. And again, your Reynolds number must be less than 2300 in order for it to qualify as laminar flow. For turbulent flow, we have to use something called the Colebrook equation. And you can clearly see just by the distinction in the different types of flow how much more complicated turbulent flow prediction actually is. Because it's so random, it becomes incredibly difficult. And you'll notice that the friction factor F appears on both the left and the right hand side of the equation. So this is actually an iterative calculation. It requires the use of either by hand a trial and error, or what you can do is you can use a function in Excel such as goal-seek, and you can determine the value of F that would make this equation stand. But ultimately this is much more difficult to find the friction factor in comparison to the laminar flow, purely on the basis of the randomization that turbulent flow brings to the table. Now, if the equation is too difficult, then an easier way of solving this is a graphical method known as the Moody Diagram. And this basically gives you a plot of the relative roughness against the Reynolds number for a wide range of different values. And the graph looks complicated to start with, but if we break it down, then we'll get an idea as to how this actually works. So what we have here is Reynolds number plotted on a logarithmic scale. So we've got 10 to the 3 here and 10 to the 8 here. Now we have a choice of different materials. It gives us a key. So this is your roughness value. Your relative roughness is the roughness of the material divided by the diameter of the material as well. So that's basically how rough is your pipe, because the rougher the pipe is, the more frictional losses you're going to experience within the system. So say for example we have a smooth pipe. So that would be this line here, this solid black line all the way up here. And say we had a Reynolds 10 to the power 5. And we wanted to know what the friction factor is for that particular system. Then what we would do is we would identify a Reynolds to the power 5, 10 to the power 5, touch the point where it intersects our smooth pipe, and then we draw along like so. And that way we can simply read off the friction factor. There is, of course, you could substitute in the values to the Colebrook equation, and you should end up with a similar value. Again, the equation will give you a more accurate value, but in ease of simplicity, the Moody diagram, you will get a rough estimate much quicker without the need of an iterative calculation. So now it's time for you to enter our monthly competition, whereby we're giving away £1,000 every month for an entire year. So that's £12,000 that you'll receive by the end of next year. And in order to enter, all you have to do is answer the following question correctly. It's, what are the vortices called that form during turbulent flow? So to enter, you simply have to comment your answer in this video, like and subscribe to the channel, and make sure that you are subscribed to our Facebook page, because that's where we will announce the winner on the 5th of next month. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of Reynolds number and fluid flow dynamics. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.
you.